Linear programming promises a specific mathematical ideal, the ability to calculate the single best allocation of limited resources to achieve a maximum or minimum objective. But relying on a static mathematical optimum carries a hidden risk. While the mathematical algebra remains perfectly rigid, the real-world business environment it represents is always in a constant state of flux. A slight fluctuation in supply costs, labor availability, or consumer demand can instantly turn today's mathematically perfect plan into tomorrow's operational liability. Because of this, calculating the initial optimal solution is not the end of the quantitative process. It is merely the baseline for a stress test. To reliably manage an operation, decision-makers must map exactly how sensitive their answer is to the unpredictable pressures of the real world. We measure this fragility using sensitivity analysis. This technique determines exactly how much an optimal solution changes when the underlying input parameters are adjusted. The signposts in this diagram outline the core objectives of the analysis: assessing the overall robustness of a solution, pinpointing critical parameters that impact the outcome, and extracting actionable insights for decision-making. Executing these advanced diagnostics requires translating the flexible language of business operations, like estimating a factory has roughly 100 hours of labor, into rigid, computable algebra. To apply standard linear programming algorithms, we must convert operational inequalities, the physical caps and minimums, into strict, balanced mathematical equations. This translation layer is known as standard form. It is the essential mathematical bridge that allows us to quantify absolute efficiency. This table details the production requirements for Flair Furniture, a company attempting to maximize profit by building tables and chairs. Each table requires 4 hours of carpentry and 2 hours of painting, while a chair takes 3 hours of carpentry and 1 hour of painting. The factory operates under strict resource caps, a hard limit of 240 carpentry hours and 100 painting and varnishing hours available each week. Simultaneously, the company must satisfy a market floor with a firm requirement to produce at least 42 total units to meet existing demand. The financial objective driving production is straightforward. Every table yields a profit of $70, and every chair yields $50. Right now, these constraints are inequalities. They describe a less than or equal to ceiling for labor and a greater than or equal to floor for demand, rather than fixed targets. While these numbers accurately record the factory's physical limits, they do not yet form a solvable problem. We must map how these variables interact geometrically. This chart maps our production possibilities. We establish the x-axis to represent the total quantity of tables and the y-axis for chairs. We plot our first constraint line here, representing the absolute boundary of our 240 available carpentry hours. Next, we overlay the second constraint line, capping our painting and varnishing time at 100 hours. Finally, we add a third line defining the production floor, ensuring we meet that minimum market demand of 42 units. The shaded polygon is the feasible region. It's the only space where all 3 operational rules are satisfied simultaneously. Coordinates reveal the optimal vertex sits exactly at 30 tables and 40 chairs, generating maximum profit. Compare this to a safe, conservative production run of 20 tables and 25 chairs, a coordinate situated deep inside the feasible region. That internal point yields significantly less profit. The geometry dictates that the optimal answer will always lie on the absolute outer edge. We quantify the inefficiency of those internal points using a variable called slack. Slack is the specific amount of a resource left unused when a production goal falls short of a less than limit. Conversely, surplus measures excess. It calculates the exact amount of production that overshoots a greater than minimum requirement. At our optimal point of 30 tables and 40 chairs, the slack is mathematically 0. Every available hour of labor is consumed to maximize profit. This chart reveals the hidden cost of our suboptimal point. Producing only 20 tables and 25 chairs leaves 85 hours of unused carpentry slack and 35 hours of unused painting slack. To standardize this mathematically, we append placeholder variables denoted as S1, S2, and S3 to our formulas. These absorb the slack and surplus, forcing our uneven inequalities into perfectly balanced algebraic equations. Written in standard form, the math serves as a strict audit. It forces management to explicitly acknowledge the exact volume of physical resources they are leaving on the table. The geometric model relies on structural logic, but specific operational errors create special cases where the math fails to provide a single actionable answer. The first failure state is no feasible solution, which triggers when management's production goals and the factory's resource limits are in direct conflict. This graph displays the geometry of that conflict. The rule demanding variable x1 be 7 or greater pulls the requirement entirely away from the area where the first two constraints overlap. The second anomaly is unboundedness. This occurs when the mathematical model dictates that profit can scale continuously without hitting a ceiling. This graph shows an open-ended feasible region expanding infinitely into the upper quadrant. There is no mathematical boundary line to cap production. A result of no feasible solution proves the goal is physically impossible. An unbounded result proves the analyst forgot to code a real-world limitation into the computer model. Operational flexibility reveals itself in the final two cases, starting with redundancy. A redundant constraint is a limit that technically exists but never impacts the actual bottleneck. This chart highlights a redundant constraint. The boundary line sits completely outside the active feasible region, having zero effect on the shape of our valid production area. While leaving it in won't change the final answer, eliminating redundant constraints simplifies the processing logic of the entire model. The most advantageous anomaly for management is the presence of alternate optimal solutions. This chart plots the geometry of choice. It occurs when the objective profit line runs perfectly flush and parallel against one of the solid constraint boundaries. Because the lines overlap entirely, every single coordinate along that specific outer edge earns the exact same maximum profit. This structural quirk grants management extreme flexibility. They can alter production ratios to accommodate employee preferences or storage logistics without sacrificing a single dollar of profit. Sensitivity analysis and geometric modeling force operators to stop guessing. They translate abstract what-if scenarios into precise operational maps. The true value of linear programming is rarely the single number it calculates. It is the deep structural understanding of the boundaries, bottlenecks, and hidden flexibilities within your business.